On Earth, we use global positioning systems to find our exact location within a few meters. We rely on a massive constellation of satellites orbiting high above the planet. These satellites send precise timing signals down to receivers in our cars and phones. The receiver calculates its position by measuring the delay from 4 or more satellites. Now imagine an Artemis mission crew on the Moon's surface without a working GPS. Earth versus Moon nav. Navigating the lunar environment is fundamentally different. The Moon has no global magnetic field to protect it or guide traditional compasses. Early Apollo missions depended mainly on Earth-based tracking and star sightings. This older method is slow, often inaccurate, and vulnerable to disruptions. As missions increase, we need a reliable system for precise lunar surface navigation. For future lunar bases and rovers, location accuracy must be within centimeters. Next, we explore the challenges of building a lunar positioning network. Why is GPS hard? The Moon's orbital distance and mass make Earth's GPS useless. Earth's GPS signals are too weak by the time they reach the lunar surface. This is because the signal strength degrades rapidly with the square of distance. Also, a line-of-sight view to Earth's high-orbit satellites is often blocked. Imagine a rover behind a crater wall, completely losing contact with Earth. The far side of the Moon never faces Earth, making direct radio contact impossible. Even a lunar constellation similar to Earth's GPS would require about 24 satellites. Launching and maintaining such a fleet solely for the Moon is currently too costly. The weak lunar gravity allows small, precise orbital maneuvers for these satellites. So, a new method called LunaNet is being developed by NASA and ESA. Current traditional methods. Traditional deep space navigation uses delta differential one-way ranging, or delta DOR. Delta DOR compares the time delay of signals received by distant antennas on Earth. The delay measures the angle to the spacecraft very accurately over time. However, this method requires large ground stations and constant Earth communication. On the diagram, we see the geometry of 2 Earth stations tracking a lunar orbiter. Another method uses optical navigation, or OptNav, by imaging distant stars. The spacecraft takes pictures of known star fields and calculates its orientation. This is highly precise for attitude, but only provides rough position estimates. Landers use terrain relative navigation, or TRN, by mapping the ground below. TRN compares real-time images to a high-resolution orbital map database. This allows a precise landing, but the system is only useful near the surface. LunaNet components. LunaNet is an architecture, not a single device or constellation. It is designed to create an interoperable internet-like network for the Moon. LunaNet provides 3 core services: communications, data sharing, and navigation. In cross-section, the architecture links lunar orbiters, surface assets, and Earth. The navigation service is based on a concept called disseminated radio navigation. This requires a few dedicated lunar positioning satellites in a stable orbit. These primary navigators transmit continuous ranging and timing signals. Other assets like orbiters and landers receive these signals and become users. Each user device on the network can also contribute to the overall timing solution. This makes the network highly robust and improves accuracy with more users. The architecture is also expandable, allowing international partners to join later. The first positioning satellites will likely use a lunar stable orbit called a halo orbit. This orbit minimizes the fuel needed for station keeping over many years. Navigating with LunaNet. Imagine a rover traveling towards the lunar South Pole. The rover's receiver acquires signals from two orbiting LunaNet nodes. It also receives a signal from a stationary surface node, acting as a beacon. These three ranging measurements pinpoint the rover's location. If a fourth node is available, the rover can also solve for an exact clock offset. This four-source solution provides sub-meter positioning accuracy. On the diagram, we track the rover's path as it moves past a major crater. The rover sends its location data back through a communication orbiter. This data is relayed to Earth, allowing mission control to track its progress. The LunaNet signals also allow the rover to automatically avoid obstacles. The network reduces mission risk by removing the dependence on a constant Earth link. Because its position is known, the rover can safely navigate in deep shadows. The system can also be used by small spacecraft launching from the lunar base. The future of lunar PNT, precise navigation, will enable long-duration surface science. Accurate location is essential for autonomous resource prospecting missions. LunaNet's architecture is a template for similar networks on Mars and asteroids. This decentralized system can evolve and incorporate new technologies over time. The first LunaNet navigation elements are planned for the year 2026. This network marks the shift from exploration to permanent presence on the Moon. So, how do we begin to build this complex infrastructure? First, an orbiter is launched to establish a reliable communications relay. This orbiter ensures that assets on the far side can always talk to Earth. Next, the first dedicated navigation satellites will be placed into orbit. These satellites will be equipped with highly stable atomic clocks. The clocks are key to generating the precise timing signals needed for ranging. Surface assets like stationary science packages will also become nodes. These fixed nodes act as reliable reference points for nearby rovers and astronauts. The entire system relies on a common, accurate time reference from Earth. This is called coordinated lunar time, synchronized with terrestrial time. The eventual goal is a completely self-sufficient lunar network by 2030. The network will then manage data and navigation without constant Earth assistance. This is the foundation for an international presence throughout the solar system. Next, we compare LunaNet to traditional terrestrial GPS architecture. Terrestrial GPS requires 4 visible satellites for a 3-dimensional fix. By contrast, LunaNet can use a mix of orbiters and surface beacons. The signals from LunaNet nodes are optimized for the lunar environment. The low lunar atmosphere allows for very precise radio wave propagation. This precision enables the sub-meter accuracy needed for landing zones. Terrestrial GPS uses signals optimized to pass through a dense atmosphere. The LunaNet design is a much smaller scale, tailored for a specific region. The cost to deploy LunaNet is far lower than replicating terrestrial GPS. The architecture is also designed to be highly secure and fault-tolerant. An important capability is real-time sharing of hazardous terrain maps. Rovers and astronauts can dynamically update the network with new hazard data. This collective mapping is crucial for the safety of all surface missions. Because the system is decentralized, a single node failure is not catastrophic. The system reroutes data and ranging signals automatically around the failure. This robust design ensures continuous operations for long-duration missions. From above, we see the complete LunaNet coverage across the lunar South Pole. The network links human-rated habitats to uncrewed science payloads. It connects small rovers exploring permanently shadowed regions. The system also provides data backhaul for high-volume science data. This ensures that complex sensor readings return quickly to Earth. The future of exploration relies on this type of integrated communication. Now let us summarize the key components of the LunaNet architecture. First, the orbital relays provide a consistent communications link. Second, the navigation satellites transmit the precise timing signals. Third, the surface nodes act as fixed reference points for localization. Finally, the user assets like rovers and landers close the loop. All these elements work together, synchronized by coordinated lunar time. This architecture solves the most critical challenge for a permanent lunar base. The reveal shows the first Artemis base establishing its own local network. The base's central habitat also functions as a powerful LunaNet node. This creates a high-fidelity local network around the human-occupied area. Astronauts exploring nearby can rely on centimeter-level positioning accuracy. This precision is vital for tasks like resource extraction and construction. The establishment of LunaNet is a crucial technological step for humankind. It enables a true multi-user, multi-mission environment beyond Earth orbit. The concept is a blueprint for future networks around Mars and beyond. This is how we are solving the lunar GPS problem and building a space internet. The age of relying solely on Earth tracking for deep space is coming to an end. A new era of autonomous and precise lunar navigation is beginning. This network ensures the success of Artemis and future deep space missions. If you want to learn more about the Artemis program, subscribe for more.